Hi everyone, this is your third video. It's titled Stoichiometry and Preparing Solutions. It should be a short one, so let's get started. As scientists, we should definitely know how to prepare solutions. It's not that hard. But to prepare a solution with the desired molarity, you have to weigh out the correct mass of the pure reagent, dissolve it in solvent in a volumetric flask, which I'm showing you right here, and then dilute with more solvent to the desired final volume. You have to really mix that solution very well by inverting the flask a couple times, and there you go. You have your prepared solution. You will be doing this in lab. Here we're just going to talk about the theory. Well, let's do a problem concerning how to prepare a solution. It reads, the anion EDTA strongly binds metal ions with a charge greater than 2. How many grams of the reagent Na2H2EDTA dihydrate with a formula mass of 372.24 should be dissolved on a 0.5 liter flask to give a 20 millimolar EDTA solution? Sounds really difficult, but it's not. All they want to know is how many grams of that reagent should be dissolved in 0.5 liters to give 20 millimolars EDTA. Pretty simple. So I would start out with your 20 millimolar because that's what they want, the final concentration that they want. So 20 millimolar really means 20 millimole over liter. I would go ahead and convert that to moles. So there's 10 to the negative 3 moles in 1 millimole of EDTA. And then I would just go ahead and convert the moles to grams. So in 1 mole of EDTA, there's 372.24 grams of EDTA. What they want is how many grams. I'm already in grams. The only thing that I have to take care of here is the fact that I have that liters on the bottom from the original concentration. All I do is basically take the 0.5 liters and multiply it to cancel out the liters, and that basically would give me 3.72 grams of EDTA. So 3.72 grams of EDTA should be dissolved in 0.5 liters to make a 20 millimolar EDTA solution. It's pretty simple. All right, let's move on. Next thing we need to review is the dilution formula. If you've taken General Chemistry 231 with me, you know that that is M1V1 equals M2V2. The only time you use this equation is if you're diluting a more concentrated solution in making a diluted solution, okay? You only use this if you're dealing with the same component. You can never use a dilution formula if you have two different things in the problem. So of course you know that dilute solutions can be prepared from concentrated solutions, and typically a desired volume or mass of the concentrated solution is transferred to a volumetric flask and then diluted to the intended volume with the solvent. So let's go ahead and try to do this problem. It should be super simple. Concentrated nitric acid has a molarity of 15.8 molar. How many milliliters should be used to prepare 1 liter of a 1 molar nitric acid solution? So I would take my 15.8 molar times, and then I would put volume 1, because that's how I want to know how much volume of that one, of that concentrated one, do I need, equals, they want to make a 1 liter, and the molarity that they want to make is 1 molar. So it's pretty simple. So 1 liter times 1 molar HNO3. So basically all you're doing is dividing 1 by 15.8. And as you see, you get 0.06329 liters, but they want to know how many mils. So I just go ahead and move that decimal place over 3 times, and I get 63.3 milliliters of nitric acid. All right, that's it. Let's move on. I want to do a more complicated dilution problem, and the only reason this is more complicated is just because you have to prepare the answer before you actually use the dilution formula in this problem. So let's read it. A solution of ammonia in water is called ammonium hydroxide because of the equilibrium that you see down here. Doesn't sound like I'm going to need any of that, but let's keep on. The density of concentrated ammonium hydroxide, which contains 28 weight percent ammonia, is 0.899 grams per mil. All right, there's a lot of information there. What volume of this reagent should be diluted to 1 liter to make 1 molar NH3? Okay, so what they want is they want to know how much of that 28 weight percent NH3 with that density do I need to make 1 liter of 1 molar NH3. So for me to use a dilution formula, I need to have them in the same concentration units. So let's go ahead and convert that weight percent into a molarity, which we actually did that in a previous video. Let's write everything down. We have the density of the NH3 is 0.899 grams per mil, and the weight percent is 28, so I'm going to just go ahead and write 28 grams of NH3 over 100 grams of solution. And then, of course, you have that density. So I'm going to start with the 28 grams of NH3 over 100 grams of solution. And I'm going to multiply that times its density. So it's 0.899 grams of solution over mil. And, of course, that cancels out your grams of solution. Next thing I'm going to do is try to cancel out the milliliters. So I'm going to go from milliliters to liters. And I know that in 1 mil, there's 10 to the negative 3 liters. All I have left, because the concentration unit that I need is moles over liters. I already have liters, so all I need to do is go from grams to moles. And there's 17.03 grams of NH3 in 1 mole of NH3. The answer for this part is 14.78 molar NH3. So that's what you're starting with. And they just want to know how much volume of that do I need to make a 1 liter, 1 molar NH3. So now it just becomes a really simple dilution formula. So you take 14.78 times V, right, V1, because that's what you're looking for, equals 1 molar, and you want to make 1 liter of it. So the answer that you get is 0.067658 liters, or if you want to turn it into milliliters, it's 67.7 milliliters of that 14.78 molar NH3. That's what you need to dilute your formula. All right, let's move on. So what if I wanted to prepare a concentration but in ppms? This is actually something that's very useful and something that I do all the time. So it's good for you to know how to do this as a scientist. This one is a little bit difficult, not difficult. This one's a little bit more challenging, this problem, so don't get discouraged, okay? We're going to work through it. All right, so drinking water usually contains 1.6 ppm fluoride for prevention of tooth decay. Consider a reservoir with a diameter of 450 meters and a depth of 10 meters. And I show you what the reservoir looks like there. If the diameter of the reservoir is doubled to 900 meters, okay, so now they're doubling it, all right? So if the diameter of the reservoir is doubled to 900 meters, how many metric tons of NaF, not F minus, are required? That seems to be a clue there. And then they give you what a metric ton is, which is 1,000 kilograms. Another thing that I'm going to give you is we need to know the volume of this reservoir. Does anyone remember what a volume of a cylinder is? It's pi r squared h. If we find the volume of this thing, that will give you a unit which is cubed. And if you remember from General Chemistry 1, one of the conversions that you always needed to know is the one that takes you from a unit of basically measurement to a unit of volume. Does anybody remember what that is? Well, if you don't, it's 1 centimeter cubed is equal to 1 milliliter. So that's what we have to do. We have to first thing is we have to manipulate the information they gave us about the reservoir and find out the volume, because the volume will give us meters cubed. We can convert that to milliliters by that conversion that I just gave you. And then if we can do that, then it's really simple actually from there. Well, there's a couple more steps, but let's start. All right, so the volume is equal to pi r squared h. They tell us that it's doubled. So the radius of that reservoir should be 450. You put pi times 450 meters squared times 10 meters. If you multiply all that out, it's 6.3617 times 10 to the 6 meters cubed. Great. So now all we have to do is convert this to metric tons of NaF. It seems like a lot, and it's actually a pretty lengthy equation that we're going to write out, but it's actually not that hard if you think about it. All we're doing is converting units. So we start with 6.3617 times 10 to the 6 meters cubed, and then if you don't know how to convert cubed or squared units, you can go ahead and ask me in class, but this is very simple. You just take the unit as it is normally, so I'm going to go from meters to centimeters, and I know that it has to be meters cubed because it has to cancel with that top, with the meters cubed on the top. So I'm going to go ahead and bracket this entire ratio and cube it. So that means that everything inside that bracket is cubed, the number and the unit. So now that meters cubed on the top is going to cancel with the meters cubed on the bottom, and I've also cubed the centimeter. So now I have centimeters cubed, which I'm going to go ahead and use my conversion now. So 1 centimeter cubed is equal to 1 milliliter. Now I go ahead and use my concentration of fluoride. So they tell me that it's 1.6 ppm, which means it's 1.6 micrograms of fluoride over 1 mil. So I can go ahead and cancel that milliliters. So now I'm in 1.6 micrograms of fluoride. All right, let's go ahead and convert that to grams. 1 microgram is 10 to the negative 6 grams of fluoride. Okay, here comes the tricky part because they tell you it's how many metric tons of NaF, not F minus, not fluoride. The concentration that they're giving you is for fluoride, not for NaF. And now you're in grams of fluoride, you've got to go ahead and change that to grams of NaF. How do you do that? The only way to do that is through moles. So you know that in 1 mole of fluoride, there's 19 grams of fluoride. So now you're in moles of fluoride. You convert that to moles of NaF. In 1 mole of fluoride, there's 1 mole of NaF. Or another way to read that is in 1 mole of NaF, there's 1 mole of fluoride. And now you're in moles of fluoride. So now it becomes kind of easy because all you do is convert back to grams. So in 1 mole of NaF, there's 41.989 grams of sodium fluoride, which all I did is just add the molecular weights of those two atoms. So now I'm in grams of NaF, and all I have to do is convert to metric tons, and that's simple. So I go from grams to kilograms, and from kilograms to a metric ton. So because I know the conversion they gave me, 1 metric ton is 1,000 kilograms. And if you multiply and divide all of that, you'll see that you get 22 metric tons. So you're going to need 22 metric tons of that NaF to treat a reservoir of drinking water that's 900 meters in diameter and 10 meters in height. This is a little bit more challenging. I don't want you to get discouraged. It's just you have to read through the problem and you have to understand where you're going. And you also have to remember certain things from general chemistry. I expect you to know all of the prefixes, all of the powers of 10. I expect you to know all of the conversions that were important back then, and that 1 centimeter cubed equals 1 milliliter is one of them. Of course, we haven't talked about the other one, but 2.54 centimeters is equal to 1 inch. That's another one. There are things that you are expected to know in this class. I hope that you get working. All right, so that's it for chapter 1. I am going to start on the math toolkit, which starts in chapter 3 for our next video. All right, guys, see you later.